All right, welcome everyone. In this video, we're going to talk about longitudinal handling qualities. So in the previous video, we talked about this mil-spec document, this 8785, that is used to, or was a combination of a whole bunch of research that correlated data to figure out the handling qualities of different aircraft. And that's related, of course, to pilot opinion. It depends on pilot opinion, and it depends on the type of aircraft that they were flying and the maneuver that they were asked to perform. And so today we're going to talk about the results of that and focus on longitudinal handling qualities. Now, these handling qualities in the longitudinal world here depend on more than what we're going to talk about today. We're going to focus just on how they're related to the two longitudinal modes that we've studied. So we're going to look first at how it's related to Phugoid properties, and then how it's related to the short period mode properties, okay? So we're going to start with the Phugoid, then go to short period. But as you'll see, it depends on more than just these two things, but we're going to focus on these two things and how they're related to handling qualities. So let's switch over here to this mil-spec document. And so again, I downloaded this from everyspec.com. You can just go online and get a copy of it. And now we're in section 3.2 here, longitudinal flying qualities. So you can see that there are the longitudinal stability with respect to speed. We're not going to talk about that. They talk about, transonic flight here. Pitch control force variations during rapid speed changes. And here we come down to this section on Phugoid stability. Okay, so the thing that they found with Phugoid stability is that you want a damping ratio. So to have level 1 handling qualities, you need a damping ratio of at least 0.04. Okay, you can have level 2 handling qualities if your damping ratio is at least zero, right? So at least positive. And then level 3, you have level 3 if you have this T2, which I believe, let me just double check here. Yeah, that means time to double. So this is the time to double. So if your damping is less than 0, that means you have a divergent mode, right? Both of these are convergent. So you want your Phugoid to be convergent, but it can be divergent and still have a level 3 handling qualities if your time to double is at least 55 seconds, right? If it's greater than 55 seconds. If it's less than 55 seconds, then you move into this uncontrollable. This is level 4. This is really bad design, okay? So, but of course, this is what we're shooting for. We always want level 1 handling qualities in every flight phase, and so anyway, these are the Phugoid requirements, okay? Now they go on to talk about flight path stability. We're not going to talk about that. And now we get into the short period mode. So that was the Phugoid. Now let's look at the short period. And the short period is a bit more complicated here. We're going to find out. So these are longitudinal maneuvering. The short period falls under maneuvering because when you're maneuvering, you're doing usually you're more sensitive to the short period response of the aircraft, how quickly that aircraft, the acceleration is related to your lift slope, as we're going to see here in a second, and that's what the pilot experiences. So the pilot is very sensitive to accelerations. Humans in general are sensitive to accelerations, right? So we notice, for example, when we go up an elevator, we notice when it starts moving because we feel this acceleration. In an aircraft, we're very sensitive to this G loading on the aircraft, and so the pilot. It's no surprise, I guess, that the handling qualities here, pilot opinion, depended on this acceleration we're going to talk about here. So here's short period response. We're going to skip that section and focus here on short period frequency and acceleration sensitivity. So what they did is they found that the handling qualities were related to the undamped natural frequency. So this is omega sub n. So this is, or excuse me, yeah, this is the undamped natural frequency. Okay, so not the damped frequency. This is the undamped frequency, and that was related to this n over alpha. This is acceleration. N is g's, so your load factor per angle of attack. Okay, so let's actually write this out here. I'm going to come down here and do it on the next page down. And then we're going to come back up here and talk about this damping ratio in just a minute. But what they have here is figures 1, 2, and 3. So let's go down to those figures and see how they correlated this data here. Okay, so here's figure 1. I'll zoom out a little bit so we can hopefully get the whole figure on the page here. Okay, so what they found is that if they plotted the natural frequency, the short period natural frequency on one axis, and what this is called the acceleration sensitivity. Let me write that down. So the acceleration sensitivity, and that's defined as well, they call it n over alpha, and what they mean by that is the change in n over the change in alpha. So this n, excuse me, is the load factor, and so we can write that as lift divided by weight. So this is actually the same as 1 over weight times the change in lift with respect to alpha. Okay, and we can put that in coefficient form. Philip shows this in his book. This is the same as writing it as 1 over CW times CL alpha. Okay, so CL alpha over CW. This is the same thing. Okay, acceleration sensitivity. So so that's what they've got here on the x-axis. That's the acceleration sensitivity, and the units for that are G's per radian. Okay. And then on the y-axis, they've got the undamped natural frequency of the short period mode. So what they found was when they correlated all of this data, to have level 1 handling qualities, you had to fall inside of this region here. And then you could go out, level 2 would be in this region here, outside of level 1, and then down into here. And then level 3, we've got level 3 down here as well. So above a certain point, notice that above this point here, these are lines with a constant slope. Okay, we're going to come back and talk about that in a second. So first of all, I should have zoomed out just a little bit more, because this first figure has to do with category A flight phases. Okay, so these were category A maneuvers that they were asked to do. But this depended on maneuvers. So let's go to figure 2. And so here's figure 2. So this is category B flight phases. So these are a different set of maneuvers. When they were asked to do this set of maneuvers, then these lines are slightly different. You notice that the bottom end here looks a little bit different. Actually, the top 2 lines are identical between these two. And it's the bottom 2 lines here that have shifted just a little bit. And then they did it again for category C flight phases, and again got slightly different results. For this set of maneuvers, again, this top line is the same, and then this line is the same here, but then they started to have different cutoffs here on the lower end, okay? And that depended on the class of aircraft. So this is classes 2, 3, classes 1, 2, and 4. Anyway, so these cutoffs down here depend on the class of aircraft. But these upper lines are very similar to what we've seen before, okay? And these 2 lines up here are identical to the 2 lines that we had in the previous 2 plots. Again, these 2 lines have shifted just a little bit, these lower 2 lines relative to the other 2 plots. Okay? So anyway, so this is again this relationship between the natural frequency and the acceleration sensitivity. Well, notice that these are on a log-log plot. Okay, so and these lines all have a slope of 1/2 on this log-log scale, which means that that if you take the ratio of the natural frequency squared divided by the acceleration sensitivity, that is a constant along each of these lines, okay? And so let me scroll back up to the first figure. So on each of these figures, they've shown this stuff over here where they've taken the natural frequency squared divided by n alpha, or n over alpha, and this is what they call the control anticipation parameter. Control anticipation parameter, and it's called CAP for short, okay? CAP. So so notice that these are lines of constant cap, okay? The cap is constant along each of these, and in fact it has this value. So it has the cap along this line is 10, the cap along this line is 3.6. We've got 0.28 along this and 0.16 along this line here, okay? So so now we can look at lines of constant cap along each of these. So if we come down here to the next figure, we see 10 here, 3.6. Those are identical to the previous plot, but then these lower bounds are values of slightly different cap here. So we've got 0.085 and 0.038. And then for this last figure, we've got 0.16 and 0.096. That's a 0.096 right there. And then again 10 and 3.6. So the upper limits on cap were the same for all of these different categories of flight maneuvers that they were asked to do, these flight phases. But the lower bounds changed. Okay, so let's just come back over to our document and summarize summarize what we know about the short period. So so we have this thing called the acceleration sensitivity, n over alpha. That's the acceleration sensitivity, and it also depended on omega n of the short period. That's the undamped natural frequency. Okay, and then if you take the ratio of so omega n sp squared over the acceleration sensitivity and alpha, this is what's called the control anticipation parameter. Okay, that's CAP. And so we can summarize the results here, what they found in kind of a table, that in order to have level 1 handling qualities, you needed now this depended on category, so I'm gonna say so category, let's see, we'll do A here, and okay, in category A, you need to have a cap that is between 0.28 and 3.6. Okay, that's to have level 1, and then for category B, you need to be between 0.085 and 3.6, and for category C, you need to be between 0.16 and 3.6 here. Okay, so that's to have level 1 handling qualities. Now, I want to point out I don't know if it's a discrepancy or what, but in Phillips's Mechanics of Flight book, he uses 0.015 here, right there. And when you go to this document, it's clearly 0.016. So I'm just going to flip back over there. This is the number we're talking about right here. To have level 1 handling qualities, category C, you've got to be above 0.16. So I'm not sure where he gets the 0.15. All of his other numbers match, so I don't know if that's a typo or what in his book. But so that's level 1. Now let's go to level 2. To have level 2 handling qualities, again, we can look at this depends on the category. And these need to be between, for A, you need to be between 0.016 and 10. For B, you need to be between 0.038 and 10. Of course, the upper bound on each of these is the same, and then 0.096 and 10. Okay, and again, I don't know what the deal is, but in Phillips's book, he uses a 0.15 right there. I'm not sure if he digitized these plots and did his numbers off of those plots instead, or I'm not sure where that 0.15 comes from in his book, but clearly in the document it's 0.16. So here we're talking about category A, the lower level. So if we go up to category A, we're looking at this number right here, and that's a 0.16. So again, I don't know where he gets his number from, but this is straight out of this document. It's 0.16. Okay, so this is kind of a summary of what was found for the short period mode, where we're looking at this acceleration sensitivity, the undamped natural frequency, and those combine into this control anticipation parameter. Okay, now let's the one thing that we skipped up here, let's go back and cover that now. So they also then found, so this short period information was divided into two things. So first it's this acceleration sensitivity, or cap. So we've got this omega NSP and N over alpha, which combine to make the cap. And that's just looking at remember, the undamped natural frequency. But of course, pilot opinion depended on also the damping of the short period. So this first section here just looks at the undamped natural frequency and neglects the damping. And so of course, here we're going to find out that their opinion also depended on the damping of the short period frequency. And that is summarized here in this table here. So assuming that we are within the limits of level 1 handling qualities on cap, basically, then you need to have damping that falls within this table here. So here we're looking at the damping ratio, and so you can see levels 1, 2, and 3. You have a lower bound, a minimum, and a upper bound for categories A and C, and then for category B, you've got a lower bound and an upper bound here. So category A and C flight phases, they come up with the same lower and upper bounds. If you're in category B flight phases, then you have slightly different bounds here. Okay, so Phillips takes this one step further, which I really like. He then plots, and I'll just kind of sketch out what he does here with these results. He says, if we're going to have lines of constant cap, and then we know what the short period damping ratio needs to be, then we can actually plot those relative to each other. So we can put the damping ratio here, so short period damping ratio on the x-axis, and then we can put the cap on the y-axis, and he plots these on a log-log plot, okay, which I won't try to draw here, but then you get these regions that are just perfect rectangles, and I'm just kind of making these simplified just a little bit, but basically, you get regions that look something like this, where you have level 1, level 2, and level 3 handling qualities if you fall inside of these different regions. And of course, so what we've assumed is that when we're talking about these level 1 and level 2 handling qualities over here that are dealing with the cap, we're assuming that the damping ratio is within its limits. Okay, so we're talking about these upper and lower limits here on cap. And we're assuming that we are within limits left and right on this plot, and then vice versa when we're talking about the short period damping ratio, those limits are also assuming that you're within the appropriate cap limits. So anyway, this is a really nice way to look at it, and I think clears it up. Unfortunately, they didn't do that in this document. I'm not sure why, because that seems kind of like a maybe an obvious next step. But in this document, they just stick with these log-log plots where they're looking at the acceleration sensitivity and the undamped natural frequency. Now, one thing I want to point out before we leave this is that these lines, we've assumed lines of constant cap here. And inherent in that, we've actually neglected these changes that can happen on the lower end. So your acceleration sensitivity, if it gets really low, these lines don't follow the same slope here. So we have these boundaries that kind of break off here. And even on the, if we go down here to this third plot, we have quite a bit of stuff going on here. So what we've assumed is that these limits that we've kind of generalized are assuming that you have acceleration sensitivities that are greater than where these points start to cut off. Okay, so we've assumed that we have acceleration sensitivities up in this region here, along the x-axis here, that it's greater than some value here. Because if you get down in this region, then it becomes a little bit more messy, and you can't just use this simplified table here that I have on the right hand side. So this table right here is this overview of what we found with values of constant cap, but these all assume that you have an acceleration sensitivity that's greater than some value so that you can use these lines of constant cap. Okay, so that's our overview of the longitudinal handling qualities. And of course, I just want to reiterate that we've only looked at the dependence on the Phugoid and the short period mode. There are other things that your longitudinal handling qualities depend on. In fact, let me just scroll down here. For example, control forces in maneuvering flight, control motions in maneuvering flight. Let's see, dynamic control forces in maneuvering flight, pitch maneuvering. So this is force gradient limits. Center stick controller, wheel controllers. Anyway, so there's a lot of other things that will affect the handling qualities in this longitudinal world, but what we've focused on are just the handling qualities related to the Phugoid and the short period mode. And now we're going to do the same for the lateral handling qualities.